The measurement of heat in a chemical reaction or some type of physical process is called calorimetry. We don't have an instrument that measures energy directly, so what we do is we're going to measure the flow of heat from one thing to another, from our system to our surroundings. The instrument to the left here is called a calorimeter. It happens to be a bomb calorimeter, which we'll get to in just a moment. Again, reminder that enthalpy is a state function. We usually don't attempt to measure the direct value for the enthalpy, but the change in enthalpy is something we would be interested in. One of the key ideas to understanding the measurement of heat exchange through calorimetry is the idea of specific heat and heat capacity. First of all, heat capacity is the amount of energy required to raise the temperature of a substance by 1 degree Kelvin or 1 degree Celsius. Their difference in their scale is equivalent. The heat capacity is defined as the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 degree Kelvin. Therefore, the formula for specific heat or specific heat capacity is the heat transferred divided by the mass of the substance and the temperature change of the substance. A couple of styrofoam cups, thermometer, glass stirrer, and potentially a top can act as a nice constant pressure calorimeter. We carry out the reaction inside an aqueous solution inside the cup and system, and we're able to measure the heat change for the system by measuring the heat change for the water in the calorimeter. And we'll do an example at the end of the presentation. The reason we use water mostly is because the specific heat for water is very well known. It's 4.184 joules per mole degree Kelvin. And so we can use that to measure the delta H for reactions. And then we've got the equation down here. Notice that the Q would be the Q for the water inside the calorimeter, which means we would need to have the mass of the water, use the specific heat of the water, and the change in temperature of the water. For more precise measurements, we can use a bomb calorimeter. Bomb calorimeters are constant volume calorimeters, so you can see over here on the left. They measure, in a more precise way, the heat that's absorbed by the water around the system. Now, the one downside to the bomb calorimeter is that because it's a constant volume, you're really not measuring the enthalpy here, because you're not doing any work on the surroundings or the surroundings on the system. So you're actually calculating the internal energy, delta E, and not delta H, or the enthalpy. For most reactions, the difference in value would be very small, however. Here's a problem involving the specific heat of a substance. The question is asking how many joules of heat are needed to raise a temperature of 40 grams of toluene from a beginning temperature to a final temperature. So this is just a straightforward application of our formula. We would have the Q that we would have to add, the heat, would be equal to the mass times the specific heat times the change in temperature that we're trying to create. So the mass is given to us, 40.0 grams. Specific heat of the toluene, 1.13 joules per gram degree Kelvin. And the change in temperature, final minus initial, so 28.0 minus 10.4 degrees Celsius. And so if we do the math here, we end up with 796 joules of energy that need to be added to the toluene to raise the temperature from 10.4 degrees Celsius to 28.0 degrees Celsius. In this next problem, we're dissolving ammonium nitrate in 60 grams of water in a coffee cup calorimeter. The temperature in this process is going to drop, so this will be an endothermic process, as the reaction is going to gain energy from the water in order to occur. And the problem wants us to calculate the enthalpy in kilojoules per mole of ammonium nitrate for the solution process. And it's telling us that we can assume that the specific heat of the solution is the same as that of the pure water. So first of all, our guiding formula will be that the enthalpy would be equal to the heat absorbed by the process divided by, looking at it for per mole of the ammonium nitrate that's dissolved. All right, so we need to figure out how much energy is added to this reaction from the water. So if we go down to, we think about the water, the Q lost by the water, or in this case it's the solution, is going to be equal to the mass of the solution times the specific heat of the solution times the change in temperature of the solution. Mass of the solution would be the combined total of the solid that we've added and the water. So that would give us 64.25 grams. Specific heat, we're told that we can use the same specific heat for water, so 4.18 joules per gram degrees Celsius. And our delta T in this case would be the 16.9 degrees Celsius minus 22 degrees Celsius, or a temperature change of negative 5.1 degrees Celsius. The net change in energy then for the water is negative 1,370 joules. Now if we take that value and wanted to plug it back into our original formula, we would end up with kind of a problem, because what we want is the amount of energy per mole of ammonium nitrate. So let's take a little step backwards and just make sure that we're thinking about this correctly. So the Q lost by the water, or the solution, is equal to the Q gained by the process, in this case the dissolving. And it should actually be the opposite, right? Which means that if the water lost energy, the process of dissolving gained the energy. So we can say that then that the dissolving gained 1,370 joules of energy per 4.25 grams of the ammonium nitrate that dissolved. Now to get this into kilojoules per mole, we would convert the grams to moles. So we have 80 grams of NH4NO3, ammonium nitrate, per 1 mole of ammonium nitrate. And 1,000 joules to 1 kilojoule. And we can check our units to make sure. Joules cancel out. Grams of ammonium nitrate, grams of ammonium nitrate. So our units are moles of ammonium nitrate and kilojoules. And we get for an answer 25.8 kilojoules per mole. Here we have an example of a calorimeter problem with a bomb calorimeter. Now this one seems a little bit different, but it's actually going to be a little bit more straightforward or simple for us. A few less calculations. So on a bomb calorimeter, remember we had our Q equals mass specific heat times delta T. Well, on a bomb calorimeter, what you do is you calibrate the entire apparatus so that the mass and the specific heat are all kind of lumped together. And so you have the Q of the calorimeter is equal to what's called the calorimeter constant, or the heat capacity of the calorimeter, times the delta T. So you can see the problem above here, we're given that value for the heat capacity of the calorimeter. We know the delta T, so we're just going to plug in and calculate the Q for the calorimeter. So that would be 7.854 kilojoules per degree Celsius. Delta T would be the 30.57 minus 23.44, or 7.13 degrees Celsius, which gives us a Q for the calorimeter of 56.0 kilojoules. So that's the amount of energy that the calorimeter absorbed. Remember that the Q for the heat absorbed by the calorimeter is equal to negative Q for the reaction, in this case the burning of the quinine. So we would say then that for the quinine we would have 56.0 kilojoules were released, negative, divided by the 2.200 grams that were put inside the calorimeter to give us a value of 25.5 kilojoules per gram. And if we wanted to convert that to moles, we have 25.5 kilojoules per gram times 1 mole of the quinine. The quinine, which is C5H4O2, is 96 grams. So we'd end up with 2,450 kilojoules per mole. So this would be our energy per mole for the combustion and energy per gram for the combustion.